We did all that work to move to the ext file system, and we still haven't solved the core problem. The core problem was that we looked at hard drives, we saw that the thing that we wanted to avoid was seeking, and so we need to do that less to have our file system be performant. ext is a little bit better than that, better at that than the FAT file system. We've eliminated the file allocation table linked list, which was a big cause of seeking in the FAT file system. But we still have our data and some metadata, in this time all of the metadata, not just where the next block is, far apart from each other on disk. Inodes are at the beginning, data blocks are at the end. And we still have nothing in place that will tend to reduce fragmentation of our data blocks. If we end up allocating a bunch of small files and deleting every other one, and then we allocate a big file, we're going to have fragmented data on our disk, and that's going to result in a lot of seeking. So the next set of optimizations that we're going to do is going to move us into the ext file system. And the idea for that is that we're going to try to improve locality and decrease fragmentation. To do that, we're going to use techniques that were pioneered at UC Berkeley in 1984 in a research project called the FAST file system. They're trying to be fast, and their goal is to, knowing how a disk works, they're going to try to make their file system work better on it. And the observation that they had is that processes tend to access files that are in the same directory. If you have a program and you're running it, it's going to open some data files in some directory, and then the other data files that it's going to open are going to be in the same directory. And if it's not going to open files in the same directory, it's going to open files that are near to it in the file system hierarchy. If we have a multi-user system, then user A is more likely to run programs that access their files. User B is more likely to run programs that will access user B's files. To do this, the FAST file system placed groups of directories and the files that went in them into cylinder groups. And the idea of cylinder groups is that if we look at the actual structure of a disk, now we don't have a picture of it here, but if we look at the structure of a disk, things that are next to each other in seek time are things that are on the same track. So you have your circular tracks, and then you have a circular track inside that, and a little circular track in the middle. And if you access data that's on the same track, you don't have to move the read-write head at all. Whereas if you access files on different tracks, you do have to move the read-write head. This isn't really helping you with rotational latency, how long it takes to rotate around, but that's a slightly harder problem. Now, the reason we talk about cylinders is because hard drives have multiple platters, and the read-write head for all the platters is the same read-write head. So if we point at track 3 of the disk, that's pointing at track 3 of platter 1, 2, 3, 4, 5, 6, however many platters we have. And so that combination of a track across multiple platters looks like a cylinder. That's why we call it a cylinder group. That's what we can access without doing any like read-write head seeking. So the idea as added to ext was called block groups. Unlike with fast file system, they didn't put quite as much effort into figuring out exactly what the layout was of a concrete disk, because in 1984 we addressed blocks by their sort of complicated address with things like a cylinder number or a track number, whereas in 1994, when ext2 was happening, we had moved to logical block addresses. And so the software didn't necessarily know which track specifically, but it did know that block number 5 was probably next to block number 6. So the idea here is that we're going to have multiple copies of sort of an ext1 style thing. So we have our super block, and then we have a series of block groups. And in each one of these block groups is sort of a complete ext1 style file system. So block group 3 here has its own pair of bitmaps, has its own collection of inodes, and its own data blocks. And if we can have enough block groups, we get to hope that maybe each block group gets its own cylinder, or at least a block group is unlikely to cross too many cylinders. And blocks that are near each other are likely to be near each other in logical block address, are likely to be in the same cylinder, and so we're going to get that cylinder group benefit out of block groups, even if they don't exactly line up with the cylinders. Now, with that, we need an allocation policy, and the idea is that it's going to try to put stuff from a directory into the same block group. And we're going to try to guess which directories are logically far apart. The example here is perfect for things that are logically far apart. We have the home directories of two different users, and those should go into different block groups. It may be that Alan's programs read Christo's files. That was our last example with the symbolic and hard links, but that's probably not the common case, and so the file system isn't going to optimize for it. Unless somehow we see that behavior and we can change. I don't know how much work got put into doing that. So ext2 is a significant improvement performance-wise on ext because we put some effort into spatial locality. Unfortunately, adding this concept of block groups has significantly increased complexity. And with increased complexity, we run into this problem where more complicated data structures are more likely to get messed up just by the normal use of the system, either because there was some bug somewhere, more complicated programs are more likely to have bugs, or because the system crashed and something got written wrong. And when the system crashes and something gets written wrong, our disk gets corrupted, and the corruption is worse and less potentially obvious. It may take longer to notice the corruption if the data structures are more complicated. So that's our next problem. So we move on to ext3. At this point, we have a file system that works. It's somewhat optimized for spinning disks, and we'd like it to work more reliably. We'd like it to work all the time. Now, there's a bunch of operations that we're going to do on a file system where we need to do multiple independent writes. For example, and this is the example that we're going to be going with for a while here, consider what happens when we append a block to an existing file. First thing that we need to do is we need to update the free data bitmap. We're adding a new block to the file, so a new block is now used instead of being free. We need to update the inode for that file to add the block to the list. And then we need to actually write the additional data to the new block. And for this picture, we're going to assume that our write is happening exactly like all we're adding is the new block. It's not adding anything to the previous block. But this gets sort of even worse if we're writing across a block boundary and part of the write is for data that was already assigned to the file, or it's for a data block that was already assigned to the file, and part of the write is to this newly assigned data block. So what we're going to look at is what happens if the computer crashes in the middle of this process of appending a block to an existing file. So let's take a look. We have our file. It's this inode. It has one data block, this one here, and the inode bitmap marks the inode that we've taken as used, and the data bitmap marks this data block that we've taken as used. So we have the three things that we need to do. We'll update the inode, we will update the data bitmap to add another block here. We haven't added the data block yet, and then we'll write out the data. Those are our three steps. Now, unfortunately, and one thing I don't think I remembered to mention last class is that hard disks and potentially SSDs are allowed to reorder block write operations. So we're doing these three operations, and even if we specify an order in our driver software for this file system, the hardware may decide to reorder those three operations for efficiency. You could imagine that these things are happening on different tracks on the platter, and so we need to seek in some order, and so we want to do it in seek order, Or maybe these things are happening on the same track. We've optimized now with block groups, so hopefully they're on the same track, but we don't know where we started in the rotation. The disk does, and so if we queue up these three operations, it's going to write these three things to disk when the appropriate block on disk goes by as the disk rotates, not in the order that we requested them in the software. The result is we can sort of model this as the three operations happen in random order. And for extra fun, if we're talking about crashes, that can happen literally at any time. The one thing that we have that makes things a little bit better is that the hardware does guarantee that block writes are atomic. So if we request that a block is written on disk, the only possibilities are the block write succeeds, and then if we crash after that, when the system reboots, the block write will have occurred, and the block won't have gotten corrupted in the process. The other possibility is the block write will not have occurred at all. And the way the hard drive, or the way that a hard drive can guarantee that this happened is actually kind of neat. You sort of have two options. You can either put a bunch of capacitors in it, and that's what you have to do with a solid-state drive, is put a bunch of capacitors so that if we have power loss, it can run off the capacitors for the fraction of a second it takes to complete the write. But with hard drives, you have another option, and that is you have this big old spinning chunk of material, and it's spinning on a motor. And if you have a spinning thing and a motor, and you stop supplying power to the motor, the thing that you then have is a flywheel, the spinning thing, and a generator. It was a motor a second ago, but it's not being powered, so now it's a generator. And so the power that you get from the disk slowing down is enough to guarantee that it can complete a block write. And that is kind of neat. Sadly, some cheap SSDs have lost us some parts of that, but we still assume that the hardware is able to guarantee that block writes are atomic. Otherwise, madness. All right, so here's some possibilities for what happens when it crashes. We're going to write the data and then crash. Think for a second. What has gone wrong? How bad is this? All right. So this is not the worst thing ever. We wrote the data, but we didn't update the inode. So the file doesn't think it owns a new data block. It thinks the data is the same as it was before. And we didn't update the data bitmap. So the operating system doesn't know that it had written the data. And so actually, this is a 100% okay outcome. We atomically did not do the write. We crashed before the write occurred. So fine. Here's another possibility. We are going to update the inode, and then we crash. Think about this one for a second. Is this one worse than the other one, or is it the same? Not a big deal. So this is sort of horrifying. So the inode is updated, which means it thinks it owns an additional block of data. The data was not written, so the additional data that is now included in this file is just arbitrary junk data, whatever was there before. And for even more fun, the data bitmap wasn't updated. So the operating system doesn't know for future block allocation, the file system doesn't know for future block allocation, that this file thinks it owns this block. So later, we may write some other file to this disk and allocate this block to the other file. And then we'll have two inodes that both think that they own this block. Now, that other file, when data gets written to this block, the data is going to get written here. So whatever other file it is, it's going to write its data here. But then if later we update this file and we change its second block, that's going to overwrite the data here. Now, this file will no longer be corrupted, possibly, but this will corrupt some arbitrary other file on disk. And that's super horrifying. This could be the operating system kernel as part of an operating system update. This could be your secret cryptographic keys that you need to not have some horrible thing happen. They're essential to your business. So this is sort of absolute worst case data corruption. We have corrupted not just the file, but some arbitrary other file at the future is also, some arbitrary other file that we're going to write in the future is also potentially going to be corrupted later. That's bad news. We would like this case to not happen. Last case, we update the data bitmap, and then we crash. Think about this one. Is this one like not a problem at all, like the first case? Is this a horrifying nightmare like the second case? Or is it something else? All right, so in this case, it is bad, but it's not horrifying. We have updated the data bitmap, so now this block is taken, it's used, but we haven't updated the data, so we didn't actually write the data. We lost the data. And we also didn't update the inode. And not updating the inode has the interesting property that the file doesn't know that it's bigger now. That means it doesn't know that it's the one who owns this, which means that even if we later delete this file, that won't result in deallocating this block. And so this block is not part of the file. We sort of atomically didn't do the file action, but in the process of that, we lost a data block permanently on this file system. So until we somehow fix that or reformat this file system, that data block is gone. If this happens one time or a dozen times over the lifetime of this file system, it's not a big deal. We can live without those data blocks. If this happens too many more times, our disk will fill up, but then we'll probably notice and go ahead and put in a new disk and reformat the original disk, and so that's fine. So the first case and the third case are not huge deals. The second case is a pretty serious problem. Our file is corrupted and our disk is corrupted. All right, more cases. I'm going to go through these quick. Two things happen. So we wrote our data block, we updated our thing, and we crash. This is the super bad case. This is super bad because we didn't update the data bitmap. So although this file wasn't corrupted, at some point in the future we're going to assign this block D2 to some other file, and we'll set the bitmap, and then this block will be shared between two files, and when this data gets written for the other file, it's definitely going to corrupt this file, and then if after that this file gets written, it will corrupt the other file, and so again our disk is corrupted in this case. Although this is potentially even worse than the other case. In the other case, there's some chance that we would notice that the file had been corrupted, whereas in this case, everything just looks fine. It looks like the file was successfully written. It's just at some point later the corruption monster is going to come and punch us. All right, update the data bitmap. This is just a block leak. There's no long-term corruption problem. The file is still its old version, and this block will never get reused, so we don't have to worry about some other file getting corrupted. Final case, we update the thing in the data bitmap. This just corrupted the one file. This data block was assigned to the file thinks it's there. We never wrote the data, so this file is corrupted, but that's the limit of what's gone wrong here. It's just we've corrupted one file. So, we have this guarantee that block writes are atomic, but we don't have any real way to make multi-sector writes atomic without slowing things down drastically. We could write one block at a time and then force a disk sync, but that would make hard disks an order of magnitude slower than they already are. We end up actually doing that in some of the file system techniques later, but we try to do it as rarely as possible. We can't do it for every block write. That leaves us with two options for trying to have our file systems be consistent if we crash. Plan A historically was don't bother to have the file system deal with it, and then try to fix it later with a utility program. So occasionally when a computer booted up, you would run the file system checker, FSCK on Linux. It was called checkdisk on Windows. And the idea is that we're going to scan the file system, try to detect any inconsistencies in corruption, and fix them. This is great unless some serious corruption had happened, in which case you may have lost critical data and still not notice even after running this tool. But there's some benefits to this strategy, and one of the benefits is that it is sort of lazier than making the data structure more complicated to guarantee or to try to guarantee consistency. Plan B is we're going to modify the way that we do file systems to try to make multiple sector writes atomic. There are a bunch of data structures that could be used to do that, but the one that got used, at least for file systems like ext4 or NTFS, is to use a transaction log. This is the same strategy that databases use to ensure that we have atomic transaction rights. It's also called a write-ahead log. And the idea is that before you make changes to your file system data structure, before you go out and do all the writes to everything, first you're going to write down a note saying what you plan to do. You're going to log what your plan is to a log. And then after you've written it to the log, then you go make the changes. And that means that if there's a crash, no matter where the crash happens, it's possible to fix it. All right, so file system checker, when the machine boots up, we're going to scan the entire file system looking for inconsistencies, and then we're going to try to fix them. So think for a second, why would we do this during boot up? The key idea here is that when we're fixing the file system, we kind of want to make sure that nobody else is writing to the file system. The reason for a file system checker is to make things simpler, and trying to have a concurrent file system checker, that's up there with a concurrent garbage collector for the sort of thing that's totally... In fact, it's even more horrifying than a garbage collector, because by the very nature of a file system checker, you're likely dealing with a corrupted data structure, and if something else is also trying to deal with a corrupted data structure, it could be making things worse as you're trying to fix it. So after the file system check runs, and we've at least made the file system consistent, we can go ahead and let the machine keep booting and do whatever it would normally do. This thing's going to have to go start at the superblock, and then it's going to have to go do several full traversals of the tree of directories and inodes and whatever. It's going to make sure that everything's reachable. If it's not reachable, it is going to throw it in a directory called lost and found and let the user figure out what to do with it. The user rarely knows what to do with it. It'll get rid of corrupted inodes. It'll make sure that directories are consistent with everything else. There's a whole bunch of work to do. So the advantage of this is that we're keeping the complexity out of the file system. And the disadvantage of this is that, well, first thing, this is theoretically impossible. You can't actually write a file system checker that will fix all the things that went wrong. Being theoretically impossible hasn't slowed down people writing real systems that much, but when it's your data consistency that is what's on the line, maybe trying to do it the way that won't work isn't the best plan. The other disadvantage is that file system checkers are kind of slow. And hard drives, which is what we were running on, are also kind of slow. And we have to do full tree traversals, which means a lot of seeking. And the thing that eventually killed the file system checker and forced people onto file systems that just didn't get corrupted to begin with, or usually didn't get corrupted to begin with, is just that disks got big enough without getting faster that when you would turn a server on, and it was servers that definitely triggered this, when you would turn a server on and it would have to scan its array of disks, even if it just has one 4 terabyte hard drive, we're potentially talking about several hours to run a proper file system check on that file system. And no, you can't have it be that sometimes when you reboot your server, it doesn't come up for 4 hours. That's not a valid thing for an operating system to say to you when you're trying to run a business. And so people didn't let it last that long. People actually finally solved the problem. There's also this stuff. All right, so the approach that we use more recently, and still on, most sort of desktop Windows and desktop Linux systems still use journaling file systems, is we're going to use a write-ahead log, and that will allow us to make our writes, even multiple block writes, transactional. So the operation that we're doing, an update to a file or whatever, becomes atomic even in the face of a disk crash. So we have to add one more thing into our file system. So logically, we'll put it after the super block, before the first block group. We'll put in this journal. So before we do any write, first we write ourselves a note saying what we're going to do. This is going to include all of the operations that we're going to do. If we then crash, there's a couple of cases. The first case is that we didn't finish writing the plan to the log. And if we didn't finish writing the plan to the log, then we just say we don't have enough information to replay this, so it didn't happen. Atomically, this operation did not occur. If the write to the log succeeded, then we know everything that we planned to do, and so we can replay that operation. Logically and atomically, the thing that we did succeeded, although we may need to do some work to finish it. So here's an example. We're still appending to a file, so we need to do 3 writes. We need to write the inode, the data bitmap, and the data. So we're going to start by beginning a transaction. So we'll write a transaction begin record to the journal. Then we're going to write our 3 things that we plan to do to the journal, and then we're going to write a transaction end block. Easy enough. Now, the terminology here is that after we're done writing to the log, we say that the transaction is committed. At this point, logically, we have completed the operation, and if a crash occurs, we'll be able to have it have happened. Before the commit point, it has not happened, and it will not happen if we crash. Once we complete the transaction, once we commit the transaction, once we've written it to the log, we're then going to go ahead and actually do the update to the data structure. So we'll go ahead and make the 3 changes to our disk data structure, and at that point we say we're checkpointed. And once we're checkpointed, we no longer need the thing in the log, so logically we can erase it. In practice, we wait a little while to do that just for efficiency, but once it's written to the real data structure, it doesn't need to be in the log anymore, once we know it's written to the real data structure. So journals are typically implemented as a circular buffer. We don't actually do erases to them. We just have a pointer to the end of them. We write to the end, and then when we get to we write to the current pointer location. And then when we get all the way to the end of the buffer, we'll just loop around and start at the beginning again. And that naturally results in the beginning of the log getting overwritten as we loop around. And yeah, so eventually it's overwritten. And then when we reboot, we need to have some record of where we start, or some way to guess where we start, and then we replay all the stuff that's in there. Now, what if we crash? Plan A, we're going to crash during logging. At this point we crash, and here we didn't write a transaction end, so we didn't commit, so we just atomically did not execute that transaction. If we get our commit to happen, and we start writing and then we crash, we committed, so then when we reboot, we'll go ahead and see a complete transaction here in the journal, and we can just replay it. So we'll do the 3 operations. Now that's redundant writes. We had successfully written the new inode, and on reboot we rewrite the new inode, but we didn't know whether we got the write done. It's not worth the effort of reading it to check. We'll just write it, and that'll be fine. Now, there is one complication, which is the complication that we were trying to solve, which turns out it ruins this whole plan. Well, until we fix it. So we're going to go ahead and write. And as you can see, we're writing different things to disk, different blocks of data, and the rule is that the disk scheduler is allowed to reorder them, so they effectively happen in random order. So we may write the end of the transaction before all the content. So let's go ahead and give an example of that. So we're going to write some data, and then we crash before it all gets written to the log. If this really happened, this would be horrifying. We go replay this transaction, and we're just going to write junk data. So we could have even successfully finished the transaction, and we reboot, and we write junk data. So the solution to this problem is that we're going to go ahead and we're going to add a checksum to the transaction begin record. A checksum could be something like a SHA-256 cryptographic checksum, if we want to be really sure that we don't get like coincidental bad results, or more likely it's going to be something like CRC64, which gives us a 1 in some ridiculously large number, 2 to the 64, chance of randomly having the checksum like incorrectly validate and throw a false positive that we had written the data correctly. So we'll read the transaction, check the checksum. If it's right, we replay it. If it's wrong, we assume it got corrupted. So this is pretty good. It means that we no longer have to deal with a file system checker. We still need to deal with a file system checker. There are still some edge cases where we occasionally have to run one, but we don't have to deal with it frequently. It doesn't have to be something that happens every 10 reboots or whatever it was historically. And with journaling, we can go ahead and recover from crashes sort of pretty quickly every time we reboot. Logically, this is pretty simple. Unfortunately, there is a problem. And the most obvious part of this problem is that now instead of doing writes once, we're doing them twice, so writes are getting slowed down by a factor of 2. There's one other problem, and that is that deletes end up being kind of tricky. So first thing that we're going to do is we're going to try to reduce the writes we're going to do. Now, one thing that we can do to make writes a little bit more efficient is that we can batch updates to the journal. Remember, sequential writes are super fast, and the journal is sequential. So the ext3 file system actually batches updates for 5 seconds. It's not going to write anything to the journal until a write occurs, and then it has waited for 5 seconds for additional writes to include in that batch, and then it's going to go ahead and blit that all out to the journal in one big sequential write. So that'll be reasonably fast, and that by itself, actually, compared to the random writes it's going to have to do to checkpoint all those things, may be enough to make the perceived write speed sort of similar between a journaling and non-journaling file system. Although when we get into SSDs, we don't necessarily want to double our number of writes because we have endurance limitations. This does have the disadvantage that if we crash within that 5 seconds, we've definitely lost all our data, but usually like 5 seconds is fine. If you were talking about having it be a 5-minute window, users would start to get annoyed at you and you'd have to turn it down, but 5 seconds is probably fine. Another trick that we can do that actually saves most of the actual writes is this idea of metadata journaling. Here's the idea. We're going to go ahead and not journal the data. We're only going to journal metadata. And the way we do that is before we write anything to the journal, we're actually going to do the data block write. Now there's a couple of cases here. If this is modifying existing data blocks, then doing the data block write is going to atomically, if we're doing a single block write, doing the data block write is either going to atomically do it or not, depending on when we crash, and we didn't actually need the metadata to begin with. But if it's multiple blocks, maybe we write some of it, and maybe this means that we have the opportunity of corrupting files, but only individual files, and only individual files that we were writing to during the crash. So that's not too bad. Once we've written the data blocks, we haven't updated the metadata, so especially in this append case, it's pretty obvious. Writing the data didn't actually modify the file. We have to update the inode to point to the new block to actually work. So then we're going to write our journal entry, which is going to include the inode data, the block data, and probably if we want to be super clever about this, we want to include the data in our checksum. I don't know whether ext actually does that, but I'm tempted to think that's the right way to design this. So then we can go ahead and checkpoint and clear our data. And this means that as long as, if we include our data as part of the checksum, then wherever we crash in here, the worst case is that we've corrupted the file, which is a downgrade from a full journaling file system where we don't mess up anything with a crash, but it's an upgrade performance-wise, and it might be a reasonable trade-off since it's more file system corruption than file corruption, individual file corruption that we were really worried about. So if we crash during logging, here, because we were only writing to a new block, this crash left us with the old version of the file and everything's fine. If this had been a write only to existing blocks, we would have crashed after doing the write, we would have successfully done the transaction, everything would be fine. If this were sort of an append where we updated an existing block and added a new one, then this corrupts the file, but we haven't corrupted the file system in any case. If the system crashes during the checkpoint, we've written the data, we write this stuff out, we update the inode and we crash. Well, this is currently we're in a corrupted state. Let's see what happens when we replay the journal. So we'll replay the journal, do both of the metadata writes, and we end up having successfully completed the checkpoint, and we're happy there too. This does require that we can guarantee a sort of ordering between the data block write and all of the journal stuff, or that we include the data block data in our checksum, but we're going to make those assumptions. Unfortunately, deletes are still tricky. So this example is sort of awkward, and I'll try to explain the awkward part as we go. So first we're going to create a directory. And the complication here in the directory is that so we wrote our data block, we put our metadata in the journal. Okay. So we're going to delete the directory. That's going to remove the inode. And we logged the delete. Now we're going to create a file. So we're going to reuse the same inode, and we're reusing the same data block. Now we crash. Now we're going to replay the journal. And here's the confusing part. Because directories are not file data, in this set of slides, we're making the assumption that although file data doesn't get journaled because of metadata journaling, directory data does get journaled. And so we'll be able to do so. Because the directory data is in the journal, we'll go ahead and replay it and overwrite it. And now we don't have the file data in the journal because we're doing metadata journaling. And so when we try to replay this, we're sort of stuck. We end up with having lost the file data because deletes are hard. And there are other examples of deletes being hard that are potentially a little bit more convincing than this. My solution here would just be don't put the directory data in the log for the same reason that we weren't putting the file data in the log. It's in a data block. But we can still work around this and solve the other delete problems as well by either not reusing blocks until the delete is checkpointed and freed. That would be pretty logically straightforward. Or we can do this idea of having revoke records. And ext3 obviously does it the complicated way. So the idea here is that when we create a directory and then delete it, before we put the delete record in the log, we're going to put a revoke record in the log. And this is saying that when we replay this, we're going to not replay transaction ID 1. This is kind of tricky because when we're replaying the log, the revoke record comes after. So in order to replay a log now, we have to scan it twice. So this has doubled the cost of log replay on every reboot, which is a cost. But reboot doesn't happen that frequently, log replay wasn't that slow, so it's a cost that we're not too worried about. So that's journaling. And that gets us to most of the features that are in modern file systems, and it gets us to the mechanism for reliability that we use in most desktop file systems. We'll talk about some exceptions to that in a couple lectures, but we actually only have one more set of parts in this story when we're talking about boring modern-ish file systems like ext4 and NTFS. There's a whole other generation of file systems that's newer that we'll talk about in a bit, but yeah, like Btrfs and ZFS. But this plan of journaling file systems works pretty well. We have good crash recovery, and the complexity, space, and performance overhead are not that bad. All right, one more thing that I want to talk about today is the final step in the sort of traditional Linux file system evolution, which is ext4. So ext4 is just adding a couple of comparatively small efficiency improvements to ext3. The first thing that we want to do is we want to solve that problem that we have with having to store inode lists. Because inode lists allow for 100% fragmentation, but that means that they allow for 100% fragmentation, and we have to store the full list of all the block numbers. And as we're getting to ext4, those block numbers are now 64-bit instead of 32-bit in order to deal with larger file sizes. And at a certain point, having 25,000 block pointers for a 100 meg file, that's a measurable percentage of the size that we're spending just on block pointers. What we can do is we can ask what happens if some of the blocks are contiguous, and it turns out that usually at least some of the blocks are going to be contiguous. And that lets us use this technique called extents. So instead of having just a list of blocks, we're going to have a list of start block length pairs. So if we're fully fragmented, then this is going to take up twice as much space as it would take with a traditional list of block pointers. But we're probably not fully fragmented, and if our average sort of run length within the file is even 3, this is reasonably efficient. And we're not looking for run lengths of 3, we're looking for run lengths of 1,000. So both ext4 and NTFS use extents. In ext4, what we're going to have is instead of having block pointers in our inodes, we're going to have some extent references, so a block pointer and then a run length. And the limitation in ext4 is that each extent can only address up to 128 megs of contiguous space, but that's still a pretty big improvement over only being able to address 4K of continuous space with a block pointer. And similar to the way we can have indirect block pointers, we can have indirect extent blocks as well. The next optimization that we want to do is directories. So we talked about directories are just sort of this array of directory entries. And so it's going to take linear time either to search for a file in a directory or to add a file to a directory. We don't want to do any of that. Instead, we're going to use B trees. So B trees are they're a search tree. They're not binary search trees. Usually they're 32-array or 64-array search trees. But this means that we can do all of our operations in log time, and the sort of locality efficiency of B trees is relatively high. They end up having a more efficient constant factor than binary search trees, because you're talking log base 32 for everything instead of log base 2. And so B trees are the solution to all the world's problems, including directories, which are just a map of file name to inode number. Now, in ext4, we're actually using a sort of clever data structure called a hash tree, or an H tree, which is the hash tree variant of a B tree. And so for this, instead of using the key as the sort order for the items in the tree, we're instead going to hash the file name, and then use that hash, this is a hash table style hash, as the key in the tree. This has the advantage of meaning that we can use fixed size structures for all these nodes in the tree. This has the disadvantage that we have gone to all the effort of building a balanced search tree, but we didn't end up with a sorted collection. And I kind of would have liked it if directories were sorted. That feels like it would be useful, but the designers decided that we didn't have that property before, so they were going to take advantage of that and keep not having that property now, but instead just make everything take log n time. So that's the only two additional features that these slides talk about for ext4, and NTFS is in sort of the same boat. And so this gives us state-of-the-art, like 2012, 2014 file systems. While ZFS is a little older than that. But what was sort of broadly used everywhere except Solaris in even 2012. So we're reasonably efficient. We're reasonably capable of handling crashes. But we can do better, and in a future lecture we'll talk more about how the sort of next generation file systems, and when I say next generation file systems, I mean copy and write file systems work, and we'll talk about which ones exist, which operating systems have them, under which circumstances, and that should be fun. Next class, I think we'll be talking about ext style file systems again, but I'll be reviewing them from another perspective because you're going to have to be dealing with them for the homework. So good luck with what you're working on currently, and see you in class.